Hello Gators, this is determining limits using algebraic properties, algebraic manipulation, and procedures. Let's take a look at some of the theorems involving properties of limits. If you know two limits, the limit of the sum of the two functions is the sum of their limits. So we can say that this is L plus M. And the same is true for the limit of the difference of two functions is the difference of their limits. So this will be L minus M. Let's go ahead and do an example here. We want to find this limit, and notice that it is a sum. So I can separate the two limits. The limit of the sum is the sum of the limits, and I'm going to allow x to get close to 1. When x gets close to 1, then this part in here will be getting close to -1. All right, and as we get f close to -1, we're going to want to use this limit, and that'll be the number 2. Plus, we're going to allow x to be close to 1 of g, and then we're going to have in the numerator 6 over 2. So this will be 2 plus 3, or 5. Let's continue the limit properties. The limit of a product is the product of the limits. The limit of a constant, so this is a constant, some number, k, times a limit as x approaches c of f of x, which will be L. We also have a quotient rule, which will be L over M. Let's be careful. We're not allowed to have the denominator equal 0. And then we have a power rule, so this will be L to the exponent r divided by s. S cannot equal 0, and if s happens to be even, the base has to be greater than 0. We have to be able to take the square root of a positive number, fourth root of a positive number, sixth root of a positive number. Let's go ahead and use these properties to see if we can evaluate this. I want to call your attention to the fact that the limit is only in this first part. This is actually just a function notation, and that's going to allow us to use this part right here. So this is going to be a 3. All right, now this is a sum. This is timesing by a constant, and we also have a product. So as x approaches 5, h of x looks like it approaches the number 5, parentheses. Then for f, it'll be a 6, plus, here's our constant, times approaching g, x approaches 5g will approach -1. And so we're going to use PEMDAS here, so that'll be a 4. And then the answer is 17. Let's go ahead and take a look at this and use the graph instead of function, the algebraic function. And so this will be getting close to f of 4. This is a composite function. You want to evaluate the inner portion first, and f of 4 is the number 1. And now when you go into 1, the answer will be -1. Let's take a look at piecewise functions. This is the left, approaching from the left. This is approaching from the right. We want to approach from the left at -5. Put a -5 in there. That'll be square root of 16, which is 4. Let's put a -5 into the right-hand side, so that'll be a -2 all over 5. Take away 25, which is -20. And so the answer is 1/10. Clearly, the left and the right are not the same, so we say this does not exist. Over here, let's take a look at the left and right for -1. So the limit as x approaches -1 on the left of g of x. I'm going to use this rule right here, the left rule, and so that'll be root, and this is going to be 10 minus 1, which is equal to 3. We'll take the limit of g of x as x approaches -1 from the right-hand side. I'll use the other side, so that'll be 26 minus 5 all over 7, which is 21 over 7, or 3. So they're approaching the same number, so the answer is 3. Let's approach E from the right-hand side. And this is going to, for E here, this is our left, and this is going to be our right. So we want to use the correct function. So this will be the natural log of E to the third, or if you want to simplify, that answer will be 3. Now that's the answer, 3. Now let's go ahead and evaluate to see if we have a limit at E, which means you have to take a look at the other side of E. And that means I have to use this rule, which is 26 minus 5e squared over 7. Clearly these two are not the same limits, so this one does not exist. All right, this is a quadratic, and let's use direct substitution to help us. The limit of the sum is the sum of the limits. This will be 1, take away 2, minus 4, or the answer is, that's negative 6, negative 5. This is a constant, so my answer is still the same number, 6. Let's substitute 0 into the numerator, and I get a 0. Substitute 0 into the denominator, I get 0. This is called indeterminate form, which means there may be an answer. In fact, there is going to be an answer if we think about it this way. I'm going to factor the numerator, and I'm going to look at this, and if I were to just put this in my calculator, I would get a line with a hole in it, and the hole is at x equal to 0. Here's where x is equal to 0. So what I'm going to do is I'm going to use a little algebra. I'm going to reduce, and now I have the same line with the hole filled in, and with the hole filled in I can use direct substitution. So this is going to be 4 times 0 minus 5, or negative 5. Let's take a look at substituting 7, negative 7, that'll be a 0. And I'm going to use my calculator, and you can see in y sub 1 I have my numerator there. And when I evaluate y sub 1 at negative 7, I get 0. So I know this is a 0. Okay, this is indeterminate form, which means don't give up. See if you can manipulate it. I'm going to use some algebra, and what I'm going to use is factoring. So I'm going to factor this, and this is going to be 2x, x. I'm going to put a 7 here and a 1 here. This is 14. I want a positive 14 and a minus 1x. And this is going to be a line very similar to the one before with a hole in it. I'm going to get rid of the hole. And now I have the line with the hole filled in. Now I can use direct substitution, and the answer is negative 1. Let's take a look at this. Let's substitute, and we're going to get a 0 down here, and here I'm going to have 36 minus 24 plus 3, and that will be 15. So this is not indeterminate, and we can't fix this. There's nothing we can do. So this does not exist. And if you were to graph it, I think you would see some places in the graph where they don't connect. All right, let's take a look at this limit. We talked about it in the last lesson, and we found that it was 1. Let's go ahead and go to the graph. I have y equal, and I have sine of x over x. So I'm just going to press graph so you can see what it looks like. And I'm going to press second calc, and I'm going to evaluate it at 0. And you can see the calculator doesn't want to give me a value, so there's a hole in the graph, but we can clearly see it looks like it is 1. Now, the reciprocal will also be 1. You can go ahead and put that in your calculator and find that's going to be true. In the end, it doesn't really matter what the variable is. It could be smiley face. As long as this, and this are all the same, then this limit will be equal to 1. Now, clearly you can see here my angle is 3x. It doesn't have just plain old x. So what do we do about that? Well, as x approaches 0, we know that 3x approaches 0. They're going to do the same thing. So what I'm going to do is I'm going to write this limit this way. 3x goes to 0. And I'm going to write sine of 3x over x. And I'm going to multiply the numerator and denominator by 3. Now, what happens now is that this angle really right here matches the denominator. And all I did was multiply the top and bottom by 3. So now this is a product. I'm going to write the limit as x approaches 0 of 3 times the limit of 3x approaches 0 of sine of 3x over 3x, which matches perfectly my smiley face idea. And so this limit will go to 1, and this limit is a constant, which is 3. So this answer will be 3. Let's take a look at this one. This one is slightly different. We have a sign on the top and bottom. So I'm going to separate this fraction. I'm going to write sine of 7x over times blank over sine of 9x. Now, as x goes to 0, I know that 7x will go to 0 and 9x is equal to 0. I'm not going to write it like I did before. I just wanted to convince you that as x goes to 0, these guys go to 0 as well. I do want to write, I want this angle to match in the denominator, so I'm going to write a 7x in the denominator, but if I do it to the denominator, I must do it to a numerator, so that's like multiplying by 1. I'd like a 9x in the numerator. Remember, I want this idea, and so if I put a 9x in the numerator, I must put a 9x in the denominator. Okay, I have a product, so I'm going to separate it into 3 limits. This is going to be sine of 7x over 7x times the limit as x approaches 0 of 9x over sine of 9x times the limit, and I'm going to simplify that and I'll just write 7 over 9, and I'm going to reduce the x's. So this limit goes to 1, this limit goes to 1, and this is a constant, and that's going to be 7/9. All right, let's take a look at this next limit, and this next limit is written right here, and I'm going to go down and I'm going to deselect this, and I'm going to go down to this limit so that you can see it, and I'm going to graph. And then I'm going to do second trace, and I'm going to evaluate it at 0. And you can see the calculator says there's no value. There's actually a hole in it, but we can clearly see that that value is 0. So this value here is 0. And this limit, the only difference is this is 1 minus cosine x, this is cosine x minus 1. And if we factor out a negative 1, we're going to have this constant here, and then we're going to have this limit we just looked at. So this answer will be negative 1 times 0, and so this will be 0 as well. Okay, let's go ahead and see if we can evaluate this. If we evaluate 0 in the denominator, this is going to be a 0, because 0 times anything is 0. The cosine of 0 is 1. 1 squared is 1. 1 take away 1 is 0. So this is an indeterminate form, which means don't give up. Go ahead and see if you can do some algebra manipulation. And so I'm going to do some factoring. This is going to be cosine of x minus 1 times cosine of x plus 1 all over x times cosine of x plus 1. And I can see that I can reduce. This is a hole, so I'm going to fill up the hole. And now this is exactly what I have right up here, and so that answer is 0. All right, let's take a look at this Let's evaluate it again. The numerator is going to be a 0 and the denominator is going to be a 0. So factoring is not going to help us, but what we can do is rationalize. So I'm going to multiply the numerator by the conjugate. So root x plus 4 plus 3, but whatever I do to the numerator, I must do to the denominator. So now I have the limit as x approaches 5, and the numerator will now be x plus 4 minus 3 squared, which is 9, all over x minus 5 times the square root of x plus 4 plus 3. Now, the numerator is actually x minus 5, so I'm going to reduce, and again, what's happening is I'm eliminating the whole, and now I can evaluate it. So that's 1 over, and if I put a 5 in here, that's root 9, which is 3. 3 plus 3 is going to be 6. Stop the screencast and see if you can multiply by the conjugate numerator and denominator for number 2 and check your work. And here is the answer. Let's take a look at complex fractions. If I evaluate the numerator, it'll be a 0, and if I evaluate the denominator, this will be negative 1/4 plus 1/4, which is 0. This is an indeterminate form. Don't give up on it. I'm going to have to use a lot of my algebra skills here. I have to get a common denominator. And so that'll be 4 times x minus 4. All right, and now what I want to do is I want to simplify this. So I can do that by multiplying top and bottom by the reciprocal. So I can multiply this by 4 times x minus 4 all over, this will be an x times 4 times x minus 4 all over x. So these will reduce, and this will reduce. And so now I have the limit as x approaches 0 of x times 4 times x minus 4 all over x, and I can reduce once again, and filling in the hole, and then I can substitute 0, so this will be 4 times negative 4, which is negative 16, and that will be the limit. Please pause and see if you can get a common denominator and go through the simplification process that's necessary. And here is the answer. Getting a common denominator, simplifying, multiplying, so that I can get the complex fraction into just a simple fraction.